Hello, everyone, and thank you for coming to Tech Talk today on day 2 of HPE Discover. And I'll be talking about AI, quantum, and HPC, how all their work together is rewriting our collective future. So this is a forward-looking statement slide because I'm from HPE Labs. You will find no more speculative discussion than the one we're just about to start in. So buyer beware, but please, let's make it a conversation about our future. Also, the reason I come to every Discover is to listen and get your feedback. Where are we doing something right? What did you wish we did instead? Let's have that conversation. So please, use your app, give us feedback. I want to know what you're thinking. So we're going to start into today's conversation. Again, my name is Kirk Resnicker. I'm the Chief Architect, HPE Fellow Vice President at HPE Labs. So I look over our entire research portfolio, everything from what goes in the next Aruba access point, the next Juniper switch, the next Cray supercomputer, the next hybrid cloud GreenLake platform or storage device, across all that portfolio. So I get to look ahead, and I want to tell you about what we're thinking about that interplay between quantum, AI, and HPC. But we're going to start with a quote. "The machine does not isolate man from the great problems of nature, but plunges him more deeply into them." This is a quote from the French aviator and author Antoine de Saint-Exupéry from his book of essays, Winds, Sand, and Stars. Some of you might know the author from his short novel, The Little Prince. But when I think about, and my kids ask me, not what you do, that's what they asked when they were little. But when they're beginning to discern their own path in life, they don't ask you what you do, they ask you why you do it. And why I am at HPE, why I'm at HPE Labs. You heard Antonio in the keynote today, to advance the way that people live and work. And for me, that is creating the tools necessary for each successive generation to solve harder and harder problems. And so when we think of the machine, here the author was thinking about his airplane, allowing him access to an area of the world that otherwise we could only dream about, to be aloft, sailing over the sands of North Africa in his aircraft. For us, it is the capability to simulate, to design, to discover what's next using systems of exploration, computation, storage, networking, AI, all pulling together. And so we ask ourselves, what is that next machine that will drive humanity forward? And what is at the heart of that new machine? And often, here we're here in Las Vegas, and people ask you, well, what should I bet on? What should I invest in? What's the next breakthrough technology? Is it AI? Is it HPC? Is it quantum? And I'm here to talk to you today about what our belief is, that it's actually all three of these. All three of these are a triad of self-reinforcing, self-perpetuating technologies. Each of them is a necessary part of what's going to come next in terms of the tools necessary for us to continue to explore, to continue to answer and provide questions to the most challenging problems that we have as a global community. Because the competition isn't between one piece of this technology. It's not just between HPC and AI. It's not between quantum and classical computation. The real challenge is, can I simulate? Can I use the tools of exploration in my computational portfolio, or do I have to? Do I have to run an experiment? Do I have to build the next generation Large Hadron Collider? Do I have to pour this chemical into that beaker and stir and bake and see what's going to come next? Or can I do it? Can I do it in the computational portfolio? Can I explore it in the process of simulation and modeling? Can I use AI and HPC and quantum all together? And that's really the opportunity, because experimentation is costly. Experimentation can be dangerous. Experimentation has side effects, and what we want to know, can I actually do this in the computer? Can I do a lifetime's worth of experiments in an afternoon in my laptop? Because that's what we've seen. computational fluid dynamics, finite element analysis, nonlinear circuit analysis, all the things that we do to create these incredible solutions of storage and networking computation utilize classical physics simulators that do exactly that. And now, of course, we can have agents that do this on our behalf. When can we do that across all the physics? And so when we think about that next generation scientist, what do we want to provide them? What tools do I want to leave behind for that next generation to be able to utilize? So whether they're a material design engineer, whether they are a pharmacologist, whether they are a fundamental physicist, whether they are a quantum chemist, what they want to have is 3 sets of technology. And I talk about the tools that I want to provide. The first, hetero quantum classical supercomputing, mastery over physics, whether that's the physics of Newton and Galileo, or that is the modern physics of Schrodinger and Dirac. I want them to have equal ease and capability to explore and simulate and design and engineer systems that behave again according to the laws of physics, the universal laws of physics, and I want to provide them mastery over those and have it happen in the computer instead of having to do that in the laboratory. The second thing we want to provide them is agentic composition. Executive agents recruiting, composing, language, energy, and physics-based models, all of those models brought together, a hypothesis agent, an operations agent, all in the aid of the sciences. Diverse data sets, instruments, infrastructure, from edge to cloud, all negotiated and obtained on terms and conditions that are in your best interest. I want to support the scientist engineer with these tools. And the last piece that we want to give them is knowledge graphs. How do we take all the knowledge, whether it's the knowledge from the literature in the library or the way that things get done here in our enterprise, and we want to incorporate that. So together, this triple, supercomputing across quantum and classical, agentic composition across resources, energy, information, and infrastructure, and finally, knowledge brought forward and incorporated into their experience as the engineer. So how do we break the quantum scaling deadlock with HPC plus AI plus quantum? How do we get to the size of quantum classical supercomputer that can tackle a real problem that we care about that? Now, I've been coming to Discover with quantum slides for 4 years now, and I've been using this one, and the good news is we're making progress. We're working our way from left to right. So when we started this, it was a kind of fuzzy picture, because that was quantum back 4 years ago when we were here in Discover 2022. It was a kind of interesting picture. We were just coming into this at Labs. We had been doing quantum research over a decade prior, and we actually put it on hold until we really realized and broke through the exascale supercomputing barrier, and then we said, we need to get back into this. We need to, because we're being asked. People are asking us, I love the exascale system, but for the one after that one, can you plug in some qubits? Can you integrate quantum processing? And the answer we thought was, we can if we partner, if we can talk and bring a community together around what we do so well, which is classical computing scaling. So small scale simulation, large scale simulation engines, multi-platform simulation engines. How do we take a problem we care about, break it apart into the pieces that should be run on the supercomputer, on the CPUs and GPUs, and what is necessary for us to run on the QPUs of tomorrow? So that's where we are. And we had the announcement, hopefully you saw on Antonio's keynote today, a collection of partners, a collection of fellow engineers and scientists bringing their quantum computational units, their quantum error correction units, their quantum estimation capabilities, along with our supercomputing networking, and beginning to explore what is that hybrid HPC quantum scaling system, so that we can work our way towards this future of a large-scale quantum computer. So this is the process that we started 2 years ago. We said the quiet part out loud. We came together, and you can see quite a list of partners, quite a number of organizations, public institutions, academic teams, national labs, our own industrial partners, and of course, HPE Labs. There might even be a Nobel laureate on that list, coming together to say and write down everything we know that we have to solve to go from 10 or 100 qubits to get to hundreds to millions of qubits. And let's write it all down. Let's talk about it and get all the things out into the open. And then the Quantum Scaling Alliance. This is that extended community that is now pledging their capabilities as researchers, as industrial development teams, as national research laboratories, and as academic institutions. Now that we've written down the to-do list, let's start doing it together. And that's really what this team is dedicated to: open research to advance what is necessary for us to achieve the scaling so that we can do the heterogeneous classical quantum supercomputer, and then augment that with the agentic systems inside and outside of the engineering and scientific laboratories, and then again also incorporate that knowledge graph together. So what is that quantum supercomputer going to look like? It is going to, at the bottom, it is going to see those quantum processing units. So hopefully you'll take some time and go up to the AI neighborhood, and you'll see, you'll see the chandelier. Actually, you'll also see a spin qubit system. You'll see a trapped ion system. You'll see a neutral atom system, and the superconducting chandeliers that are so intriguing, beguiling, and beautiful, and also phenomenal capabilities of engineering to create systems that operate at 0.01 degrees absolute Kelvin above absolute zero, and that's what we've been able to engineer. So bringing all those pieces together, so we'll be the low-level quantum systems, and more than one kind, because they all have strength. They all have pieces of the solution to problems we care about, and we actually want to bring in and want to have all of those types of qubits made available for problem solving. A quantum interconnect, that's in our farther future. That's going to build upon both our understanding as a phenomenal networking community, as well as our labs research into photonics. How do we extend the quantum entanglement from QPU to QPU between types of QPUs? That's farther out. Until then, we'll rely on high-performance supercomputing networking, on our Juniper networking, all that to stitch this together. The quantum controller, this was two more partners that we announced today. Qblox Quantum Machines, teams that are engineering what sits between the classical domain and the quantum domain, between digital electronics and microwave and laser electronics, capable of manipulating the physical systems inside of those QPUs. Above that, that's where comes in the HPC. So much to calculate, so much to think about. And again, as we attack a problem that we really care about, it's not just a quantum problem. It's going to be an AI problem, it's going to be an HPC problem, and that's where all that comes together. And finally, all of that networking, connecting not only the quantum classical supercomputing elements together, but then connecting out to the scientists, out to the engineers, out to where all that data wants to live. So let's dive a little bit deeper into how all of these pieces are going to come together. So we're going to start from the bottom and they grow up, and I'm going to highlight every time that HPC and AI are going to enable the next piece of what needs to come together for a quantum solution. So let's start at the very bottom. Multi-physics design and simulation. Wafer scale quantum processing units operating at or below individual Kelvin degrees above absolute zero, each which has hundreds of thousands of quantum devices, all being manipulated by either microwave radiation or laser pulse. That is an incredible engineering simulation. How do you design something that is that complex that works in the quantum domain? That is where electronic design tool automation augmented with AI, AI in the tool, AI in the generation of those tools, and then so much computation in order to engineer how to design that wafer scale accelerator. The next level up, semiconductor process. Now we have a design for that wafer scale QPU. Now we need to fabricate it. And so that next generation of fabrication efficiency to get the accuracy, the repeatability, because I need every one of those hundreds of thousands of qubits to perform well, to perform in concert with all of its entangled pairs. Any one that is a problem is going to, unfortunately, Can it affect all the other entangled qubits? I need to have that next generation manufacturing capability come together. Again, HPC AI in the fabrication to improve the yields and improve the wafer scale correctness and accuracy of all those QPUs devices. The quantum processors themselves, and again, this is where HPC and AI will enable these teams to create quantum systems that we can manipulate, that we can engineer, and we can scale. Above that, the control. Again, this is that dividing line between the quantum realm and the classical realm, between the quantum and the digital, and understanding how we work with the teams necessary here to create those incredibly accurate analog radio frequency and analog laser pulse control ASICs that can turn the quantum assembly language into the electromagnetic and laser pulses which actually enable us to execute a quantum algorithm. Fault-tolerant quantum compilers, distributed error correction, high-performance control and calibration, real-time control of these quantum systems will demand operational efficiency that really can only be achieved with the union of high-performance computing and AI. These have to be operated at superhuman levels of performance, and that is where AI shines. Our ability to create cyber-physical control systems, agent control over cyber-physical systems is some of our fundamental labs research that we're demonstrating today at Discover, and I invite everyone to take a look at it. Exascale infrastructure, and this is where we meet the scientists and engineers. Because where are those scientists and engineers? They're at the supercomputing center or they're in the laboratory. We're hoping to get them out of the laboratory and into the supercomputer center even more when we augment that capability of supercomputing, of solving the ordinary differential equations of classical physics with the Schrodinger equations of quantum physics, but still bringing all those CPUs, the GPUs, and fabric together. And then how do we take a problem, take all these interesting problems of drug discovery, of condensed matter physics, of material science, and turn them into a problem that can be broken down into quantum and classical, and then run efficiently over all these resources. That is where our understanding of today's supercomputer over heterogeneous classical compute will aid us to participate in this next generation. And finally, the applications. So from the top down, understanding how we meet the engineers and scientists of today, who are, the majority of applications that we're seeing run on the exascale systems have to do with quantum properties, with quantum behaviors. Now, we want to be able to take today's applications and run them better, but also to anticipate tomorrow's applications. What's beyond the current set of algorithms, what will be new and could only be realized when we create this quantum classical system that is augmented with AI, that is complemented with the knowledge graph that is bringing together all of those agents in service of science and presenting that environment to our customers. So how is this going to come together? What should we expect? The number one question I've got this week is, where's the first win? Where is the first place that we're going to look at something and say, you know what? That's worth a Nobel Prize. That's worth a patent. That's worth founding a new startup, and we couldn't have done it before, but now we can. And that's part of our prediction. Maybe when we come back for Discover 2030, we'll be talking about that new startup. We'll be talking about that new discovery and where should we expect it. So what we think about is drug discovery. Think about, this goes back to Richard Feynman. He told us we wanted to simulate nature. It better be quantum mechanical, damn it. And he also told us it was going to be a really hard problem. Right, I think, on both accounts. So when we think about what's coming next, we think about that unified application, that we're going to have these utility scale quantum systems, but the first job they'll do isn't to solve the whole problem, because they still probably won't be big enough. But what they can do is they can generate data. So they can generate massive amounts of quantum behavioral data that will augment, and we can compare to that which we got out of classical, to that which we get out of physical experimentation, and we will extend that body of knowledge, and then that will most likely feed into the next generation of physics-informed machine learning. So that's how we're going to scale. We'll start with quantum simulation. We'll use it to complement what we already understand from physical experimentation and classical simulation. We'll generate the next generation of AI tools that are inspired by quantum mechanical behavior, and that's what's going to come and generate an actual outcome. Most likely, my bet is drug discovery. So, I want to thank everyone for their attendance. We have so much more at HPE Labs to show you. So right behind you, you'll see Celebration 60 Years of Excellence, our labs area in the emerging technology. Please come afterwards, meet the labs attendees, meet me, and we'll take your questions there. Thank you.